Wow, the screen is huge. My advisor looks scary now. Thanks, Facebook, for hosting the event. I am Ashwin. I'll be giving a talk on incorporating structure into language models. This is joint work with Siva Reddy and Chris Manning from Stanford. So I chose language modeling as a task to introduce a new kind of method, and I think it's a nice task because it's kind of self-contained. Now, let's look at the motivation, and then we'll go over to what kind of structure we want to introduce. So the motivation is that we know RNN LSTMs can model language pretty well, and then they also have theoretically an infinite context that they can hold in memory. But however, in practice, they have a limited long-term capacity. For instance, if you take the sentence, when reports of an imminent agreement circulated, the circulated word uses hidden representation of agreement and so on. However, linguistically, reports is responsible for generating circulated. Unfortunately, the words are off. So to see this, just remove a chunk, the chunk of an imminent agreement, and you'll see that the resulting sentence is valid and subsumed by the original sentence. So the idea is to empower RNNs by providing skip connections over optional chunks. And for this purpose, we have a tree structure called optional constituency trees, which is a hierarchical structure which identifies constituents which are contiguous spans in a sentence that are optional. For instance, in this case, the spans inside the bracket are optional. So once we have defined the tree structure that we want to introduce, the model itself is not very difficult. So the bracket RNN, which is what I call it, processes the brackets linearly along with the input words from left to right. So before encountering a bracket, it just goes along as it usually would have done. When it sees an opening bracket, it takes the current hidden state, in this case, the hidden state after reports, and pushes it or saves it onto the stack. Similarly, right before imminent, it also saves the current hidden state. Now, when it encounters a closing bracket, which is when you would have wanted the hidden state of an, it pops off that hidden state, merges it with the hidden state of the current word, which is imminent, and then tries to give probabilities for the next word, which is agreement. And similarly, when you want to predict the word, probabilities for the word circulated, it merges the hidden states of report and agreement. So you can see the model has a choice when it wants to merge in terms of how much information it wants from the current context and from the previous context. Yeah. So we did some preliminary experiments to see how well does this, like what's the upper bound on the improvement that we can get by introducing such a kind of structure. So we took goal dependency trees and applied heuristics to convert it into optional constituency trees. We mapped dependency arcs such as subject to required and oblique to optional and so on. We provide this optional constituency structure to the language model, and we use AWD LSTM as a baseline, which has shown strong performance on the Pentry bank. So we see that if you, for instance, had one layer, you can't see the test perplexities here, but the differences are almost the same. So the validation perplexity for one layer goes down from 90 to around 70, and less perplexity is better. Similarly, for 3 layers, the validation perplexity decreases by around 12 perplexity points. So the future work is going to be to compare optional constituency trees with other structures such as random bracketing, self-attention, and balanced binary trees. And more importantly, to learn a joint model for left-to-right language modeling along with incremental OCT parsing, the kind of structure that we were wanting to use. If you are interested in introducing different kinds of structures and different kinds of tasks, please come and talk to me in the poster session. Thank you.